Okay, so in this lesson I'm going to look at a D block element. So that's an element that is within here on the periodic table within this blue region here. And it's called a D block element because the outermost electron for all of these elements will be within within one of the D sub energy levels. So wherever it ends up. So what I want to do is I want to look at one example here, and that's iron. So iron is an element that's within this D group. So we can see here if we look at iron, its atomic number is 26. So that means it has 26 positive charges within the nucleus of within its nucleus. So it has 26 protons within the nucleus within its nucleus. So what we kind of want to look at then is we want to look at if it has 26 positive charges coming from these 26 protons, it also has to have 26 electrons. So that's 26 of these guys. So what we want to try and figure out is how are these 26 electrons configured or arranged in the space outside of the nucleus within this space here. So what we do is we fill up our sub energy levels as per these three particular rules here. So the first rule states that electrons will occupy the lowest energy sublevels first. So you have to fill up these lower, like this sublevel here is filled up before this sublevel, and that's before this one, etc. Not more than 2 electrons can occupy an orbital at any one time. So each of these dashes here, so here, they represent an orbital. They represent a suborbital, and each of these can hold 2 electrons only. So each dash or each line can hold 2 electrons. And electrons tend to occupy orbitals of equal energy in singly where possible. So what that means is that, like when, for example, the 2p suborbital is being filled, 1 electron will go into each one first, and then if there's any left over, they'll double up in each one. But what will happen is they will fill these energy levels singly before they start to double up and fill up each of the orbitals. So with that said, let's look at first of all we'll arrange the electrons within each of these orbitals, and then what we'll do is we'll write out what the electronic configuration is for iron. So what's going to happen is you're going to get, so 2 of these are going to be within here. So you're going to get 2 electrons here. So that's this energy, sub-energy level filled up. The next one then is going to be this one here. So you're going to get 2 here. So that's that one full up. And then within this one, this can hold a maximum of 6. So you have 2 here. So you're going to have 2 here, 2 here, and 2 here. So within the 2p orbitals, you're going to get 6 electrons. So you're going to get 1, 2. So that's going to be completely full. Then within the third energy level, the s orbital, you're going to get 2 more in here, like so. And then within the 3p orbital, you're going to get 6. So the way, like, if you think about when the electrons are filling up this orbital, so they'd go in like this 1, 1, and 1 first, and then if there's more left over, they'll double up like this. So you've 6 there. Then within the 4s energy level, you're going to have 2. So this is going to fill up. And then what we're going to start doing then is we're going to start filling up. And notice as well that this 4s energy level is of lower energy value than the 3d energy value. So this one here will be filled first. And then within the 3d then you have you're going to have the 6 remaining electrons. So you're going to get 1, 2, 3, 4, 5, and then what will happen is this one here will fill up 6. So it'll look something like this. So this first orbital is completely full, and then these are singly filled as well. So this kind of goes in line with these principles here. So this Albury-Fuhrer principle states that electrons will occupy the lowest energy sublevels available. So they'll start filling up from the lowest energy levels available. So we start down here and we work our way up. So not more than 2 electrons can occupy an orbital at any one time. So within each of these suborbitals, you have, within each of these orbitals here, which is represented by the dashed line, you can have a maximum of 2 electrons. And electrons tend to occupy orbitals of equal energy singly where possible. So for example here, instead of these doubling up, what they'll do is they'll fill everything singly, and then whatever's left over they'll double up, just like what we've seen here. So then what we want to think then is, how do we write this? So this is the way that visually this is what happens, and it's how the orbitals are filled up with the electrons for iron. But we want to be able to represent this and write this out. So how do we do that? So first of all, we want to represent this guy here. So we just simply write it as, it's going to be 1, which represents the first energy level, S, which represents the type of orbital. So this is this S orbital. Remember, S orbitals are kind of they're spherical, and then within that you have 2 electrons. So you put this superscript up here. So that represents these first 2 electrons that we have. Then we move up here to the next one. So we have this one here. So in the second energy level, you have 2 sub-energy levels. You have the 2s, and then you have the 2p, and there's 3 of those. So you're going to have 2s, and then you have, it's full, it has 2 electrons. So you put this 2 up here. Then you're going to have the 2p, and you have 6 electrons, 2 in each of these p orbitals. So that's going to be 2p6. Then you have, so that's those ones. And then, if I just change the color, then you have this s orbital, so 3s. So you have 3s, and within that you have 2 electrons. So it's 3s2. So that's that one. Then you have 3p, and it's full. You have 6 electrons in each of those p orbitals. So then you have 3p and then a 6. Then we have the then we have this guy here, which is the 4s. So we're going to have, let's just make some space over here. So you have this 4s, so that's going to go in here. So 4s, 4s, and then you have 2 electrons. So the 4 represents the fact that it's the 4th energy level, and then within that you have a 4s sublevel, which has an s orbital, and it has 2 electrons in it. And then this outside, this final group of electrons is contained within this the 3d sub energy level. So it's going to be 3d, because that's this here. And then you write down then the number of electrons that are there. So you have 1, 2, 3, 4, 5, 6 electrons. And notice as well that, you know, these are the outermost electrons. So when there's a chemical reaction involving iron, it's going to be these reactions, it's going to be these electrons here that will come into contact with whatever they come into contact with. And we notice that these outside electrons then, or the outer or the valence electrons, are contained within this d orbital, and that's why it's called, that's why it's known as a d block element. So that's iron, for example, and that's how you would, that's what it looks like. So within the d block elements as well, there's these 2 particular elements here. So you have copper and chromium, and these 2 are kind of an exception, so they are as well. And what I mean by an exception is the way that they fill up, or the way that the electrons are arranged within on the within their outside of their nucleus, for example, is just slightly different. And I just want to kind of just highlight that as well, just so that you're familiar with these two as well, because they are just slightly different. They don't follow the rules exactly, and they are a little bit of an anomaly in relation to this system that we've been looking at. So if we have a look here, so this is the way these elements kind of pan out. So what we would expect copper, for example, its electronic arrangement would be something like this. This is the way we would expect it. What actually happens is this is the way it actually arranges itself. So let's kind of just look at what that looks like for copper here. So copper, so you're going to get 2 electrons here. Okay, this energy level will fill up. Then we move up to the next energy level. So this fills up. So we have 29 electrons. Then if we look at the P, so this fills up as well. 1, 2. So with this one, then we have the 2p. So that fills up. Then we have the 3s. So this completely fills up. And then we have the 3p's. So these fill up as well. Then we have 4s. So what happens is 1 electron goes in here, and then the remaining 10 they go in here. So that's 10. So this is kind of unusual, because what we would expect is that one of these guys here should fill up this energy level here. But when we look at copper and we look at the way it actually fills up, this is the way that it fills up. So what happens is this, even though it's a lower energy level and it doesn't completely follow this principle here, because some of these electrons, for example, are, this is completely full while a lower energy level is left unfull. This is the way that copper, for example, copper is just a little bit different, and this is the way it fills up like so. And the same with chromium as well. We would expect it to fill up like this, but it actually fills up like this. So let's have a look at that one and how that one works. So first of all, you're going to get, so this first energy level is going to be completely filled up with 2. So that's that one there. Then we have the 2s, that has 2 in here as well. That one. Then you have 2p, so it fills up as well completely. Like so. Then you have the 3s, so this one here fills up completely. Then you have 3p. So this one fills up as well. And you 4s. So what actually happens is you get 1 electron in here, and then you have this 3d, you have 5. So you get 1, 2, 3, 4, and 5. So it kind of fills up very differently than what we would expect. So what you get is you get this kind of arrangement. This energy level and these 4 energy levels here are filled up singly. So instead of, let's say, one of these, what we would expect following the rules is that one of these will come down here and this will be completely full. But that's not the case with chromium as well. So these are just 2 kind of anomalies just to be aware of as well when we're talking about D block elements. Now what we notice as well, again, why are these D block elements? So these are D block elements because the outermost electrons, which are these guys here, they are contained within the orbitals, like so, and hence the name, or hence why they're known as D block elements. And any element that shows up here within this group is known as a D block element. So hopefully that makes sense. And again, it's just to be aware of these 2 particular elements within the D group because they are just slightly different. We would expect them to kind of fill up this way, but they don't. They actually fill up just slightly different as well. Okay, so hopefully that makes sense, and thank you for listening.